Hi, class. So this is our second lecture in chapter 16 on thermodynamics. And in this lecture, I'm going to go over section 16.3 on the second and third laws of thermodynamics. So let's get started. Share my screen with the PowerPoint on chapter 16.3. So in this chapter section, the goals are to state and explain the second and third laws of thermodynamics, and then to calculate the entropy changes for phase transitions and chemical reactions under standard conditions. So as we go through, you'll understand what all that means. So first of all, let's look at some terms that we're going to use. You've heard of some of these before. So first is the system. And we're going to define the system as the part of the universe that is undergoing this process. It could be a chemical reaction, it could be a phase change. Those are the two typical chemistry processes that we're talking about. Secondly, we want to define the surroundings, and the surroundings are everything else. We could say that is the same as the rest of the universe. Sorry for the little beams. I don't know if you can hear them. So it's everything else outside the system. So there's a little note here that says generally chemists just focus on the immediate surroundings, but it really is everything else. So our system is just a little tiny speck that's a point in the universe that is undergoing this process. And what we're interested in is what's going on with that system and how it interacts with the surroundings. So with these terms defined, we can define the universe. It's the system plus the surroundings. So that's the whole thing, in other words. So to correctly predict the spontaneity of a process, we have to consider both the entropy changes that are going on in both the system and the surroundings. And that would be described by this equation where we'd say the entropy change of the system plus the entropy change of the surroundings is equal to the entropy change in the universe. So the entropy change of the universe is the sum of the entropy changes for the system and the surroundings. So the second law of thermodynamics states that all spontaneous changes cause an increase in the entropy of the universe. So this is the second law. It's a law that, remember, laws come from observations of natural phenomena. So this is where this law comes from. It states that all spontaneous changes cause an increase in the entropy of the universe. So another way to look at this is that if the delta S universe is greater than 0, it means the change is going to be spontaneous. Now this, remember previously we talked about changes in entropy as being spontaneous for a system, that it's a strong indicator of a spontaneous process if a system has positive entropy. We also talked about if a system has a negative enthalpy, it's an exothermic, that's a strong indicator of the spontaneous process. Well, now what we've done is, we'll look at this later, we try to combine those things and group them together into what's going on in the universe. So when we say if there's a positive change in energy or entropy in the universe, if the delta S universe is greater than 0, that's a spontaneous process. So that's an absolute statement. It doesn't matter what's going on with the with the entropy of the system, or the entropy or the enthalpy of the system. If the entropy of the whole universe changes, if it increases, the process is spontaneous. Conversely, if the entropy change of the universe is less than 0, that would indicate this process is not going to be spontaneous. And lastly, if the change in entropy of the universe is 0, that means the process is at equilibrium. So you have to keep these 3 different types of entropy changes clear. The universe is kind of overall arching, that's controlling the spontaneous process. The system can have an entropy change, and the surrounding can have an entropy change. Let's go back to our, well, let's look at an example. Oh, here's the third definition, that the energy tends to disperse from areas of high concentration to areas of low concentration. That's another way to think of the second law of thermodynamics. So the definition of entropy is delta S equals Q, it's the heat of a heat change in a reversible process over temperature. So we've taken out the temperature in this. So the temperatures that this heat change is occurring at determines what the entropy is going to be. So let's look at this example that we had previously. Remember the hot block and the cold block? So X is the hot block, Y is the cold block. And what we know about that, that means the temperature of X is greater than the temperature of Y. We're going to put them together. And what we always observe is that heat is going to flow from the hot block to the cold block. And so let's assign the change in entropy of the system to one of these blocks, and we'll assign the change in entropy of the surroundings to the other block. And this makes sense because you don't have to just put 2 hot blocks together. We know that if we have a hot block just out in the air and air temperature is cooler than the hot block, the block is going to cool down. So if you just had a hot block outside in the universe and it's hotter than the universe, you know that hot block is going to go down. So in this case, we're going to assign the cool block the delta S for the surrounding. That's going to be for the, for the surroundings. So what I was saying before, if we have a hot block just out in the air and the air is cooler, the air is the surroundings, sorry. The hot block is the system. So in this case, we're going to assign the hot block the system and the cold block the surroundings. So we know the heat flows. That's our observation. That's naturally what always happens. So we're going to say, we're going to give the sign of the heat change a minus Q for the system. This is going to be the hot block. We'll give it a plus Q for the surroundings because we know heat's going to go from the hot to the cool. This is a mistake. I said consider the hot block the system and the cold block the universe. That's wrong. It should be the cold block is the surroundings. Sorry about that. I'll fix that when I post this slide. Because the T of the system is greater than the T of the surroundings, well, since we're dividing by T, we're dividing the heat change by the temperature. Because T6 is greater than T surroundings, it means that the delta, the entropy change for the system, T is bigger. When you divide by a bigger number, you get a smaller quotient. So the heat change is the same. That's why we have minus Q reversible for the system and plus Q for the surroundings. So that is constant. Heat change is the same. When we did calorimetry experiments before, you know, we looked at heat change between the system and the surroundings, and that's how we look at the heat change is that the heat loss from the system is equal to heat gain of the surroundings, or vice versa. But the temperature is different. So since the system has a higher temperature, it means the delta S for the system is going to be smaller than the delta S for the surroundings. So that's what I said in statement 3 here. The delta S for the system is less than the delta S for the surroundings. That comes from the fact that the temperature of the system is greater than the temperature of the surroundings. So what does that mean? When we add them together, remember the delta S for the universe is where you add these together. Well, if you add, and the sign is different. The delta S for the system is negative. The delta S for the surroundings is positive. So when we add them together, it means the delta S for the system plus the delta S for the surroundings is going to be greater than 0. So if you have a little trouble, if that's not quite making sense to you, give these numbers. Say the delta S for the system is a -3, and the delta S for the surroundings is a +4. In magnitude, it's a little bit bigger. You add them together, you get a +1. That's greater than 1. Therefore, the delta S for the universe is greater than 0, and the process is spontaneous. So that's an example. And for any spontaneous process, if you compare the change in entropy of the system with the change in entropy of the surroundings, add them together. If it's spontaneous, the entropy change for the universe will be positive. And that's what the second law of thermodynamics says. Okay, on to the third law. And the third law gives an absolute value for the entropy. It says the entropy of a pure and perfect crystalline substance at 0 Kelvin is 0. So this is an absolute scale. So 0 Kelvin is called the absolute zero scale. And this is an absolute scale for entropy. Since there's no lower temperature than 0 Kelvin, you can't get any lower entropy. So at 0 Kelvin, all molecular movement stops. And there's only one possible way to arrange the molecules. And we're going to say that the entropy of that substance at absolute 0 is 0. Well, what that allows us to do is to make an absolute entropy scale. So here's some standard entropies for different substances, and every substance you can determine entropy for every substance. So here's a few. There's entropies of elements, and there's entropies of compounds made from those elements. So let's go back a little bit. Okay, because of the third law, it's possible to determine the absolute entropy of a substance. And what's been developed are these things called standard entropies of substance. So the standard entropies are the entropies not at absolute 0, because they're all 0, but at a given condition. In the given conditions, we talked about previously what standard conditions are. In the case of standard entropies, it's 1 mole of substance. And that makes sense because remember, entropy is a state function, which means it's an X has the property. If you go back, remember I described what state functions are and all the qualities of a state function. Remember, one of those was that it's an extensive property. It depends on the amount of a substance. And for the standard entries, the amount is 1 mole. However, you have to keep that in mind whenever we do calculations using standard entropies. You have to keep in mind how much we're dealing with. If it's not 1 mole, you have to make a correction for how much there is. So we'll see that. We'll go back and look at that table. We'll look at the units of entropy that make up the standard entropies of substances. So anyway, the amount of the substance when its standard entropy is given as 1 mole. The pressure is at 1 bar, which is about 1 atmosphere. And the temperature is 298 K, which is 25 degrees C. Sometimes it's 0 degrees C. In this case, the standard entropies are defined at 25 degrees C. And for aqueous species, you know, where there's the phase has a little subscript AQ in it, the concentration is 1 molar. So the standard entropy values can be used to calculate standard entropy changes for a process. So let's see how that works. So here's our table of standard entropy values, and you'll see it's the standard entropy has a superscript, a little 0 superscript. That means it's a standard entropy. The temperature is given, it's at 298. It's in joules per mole per Kelvin. Joules per mole per Kelvin. And the joules per mole, remember that's what we said with units of entropy previously, but since this is 1 mole, this is entry of 1 mole of substance, the unit is joules per mole Kelvin. So the equation for calculating standard entropies of a process is similar to that for calculating standard entropies per process. So it's just the sum of the entropies of the products minus the sum of the entropies of the reactants. It's like what we had to do for enthalpies. Remember, this was called Hess's law. Talked about that previously. He said we're going to apply Hess's law to entropies. We're also going to apply it to a new thermodynamic function that we're going to learn in the next chapter called Gibbs free energy. So Hess's law is important, and how you apply Hess's law is important. So one thing you have to remember is to multiply the standard entropies of the substance that we're using in this equation by the coefficients of the balanced chemical equation. Because, and I have in parentheses, because the standard entropies are per mole, remember the coefficients say how many moles are involved in a chemical reaction. You also have to pay attention to the phase. So it's not just the formula, but it's the phase, it's the solid, liquid, or gas phase that the substance is in, because each of these have different standard entropies. If we go back, I think there's one example, look at water, gas, water and liquid phase. So the gas phase, the entropy, standard entropy of the water in the gas phase is 188.71 joules per mole Kelvin. And the standard entropy of the water in the liquid phase is 69.91 joules per mole per Kelvin. So when you're doing a calculation, you have to pay attention to this subscript. So that's it for the PowerPoint. I'm going to turn off the screen share and switch to our worksheet, which is worksheet 23. So I hope you can see that and bring it into focus. Maybe I'll brighten it a little bit. Oops, darkening it instead. There we go. So worksheet 23 talks about qualitative predictions of entropy change. And it shows, there's a little description there about what to do, but it basically we're going to be using this formula to calculate the entropy change for a chemical reaction that we just saw in the PowerPoint. Going to be looking at the sum of the entropies of the products minus the sum of the entropies of the reactants. And at the bottom of this table, when you look at this worksheet yourself, you do it yourself, there's a table at the bottom that has those standard entropies, the same table we saw in the slideshow. So there are two things you need to do here. One is to just qualitatively predict what the entropy change is going to be. We did that previously in the last worksheet. So I'm going to do problem 1. I'm going to let you do problem 2. So in problem 1, we have methane plus oxygen going to water plus CO2. Well, methane is the same as natural gas. So this is a combustion reaction of methane. The what we see is that on the left side, we have methane in the gas phase, oxygen in the gas phase. If you didn't look at this carefully, it looks like we have 1 mole on the left, or 2 moles on the left and 2 moles on the right. So it would be hard to predict what's going to happen, other than if we look at the subscripts, it makes it a little bit easier because the water in this reaction is in the liquid phase. So this is a case where, I don't know, if you actually did this reaction, water would be in the gas phase, not in the liquid phase. But in this stated equation, it shows that water's condensing when you do this reaction. And so my prediction, my qualitative prediction, is that because the reactants are all in the gas phase, and in the reactant phase, we have 1 in the gas phase, 1 in the liquid phase. We know liquids have lower entropy than gases. And so I think that entropies of this process is going to go down. So I would predict that the delta S for this process, now this isn't whether it's spontaneous or not, this is just the delta S. Remember, the spontaneity has to do with the temperature that this is occurring at, and it's the delta S of the universe. So we're not calculating and predicting the entropy of the universe, we're predicting the entropy of this system. So my prediction for this system is that the entropy is going to be negative. So I would say the delta S of the products, and this is the delta S of the reactants. My conclusion is that delta S of the products is less than the delta S of the reactants. Oops. Let me get rid of that. This is supposed to be reactants. So reactants. So since we're doing products minus reactants, and products is less than reactants, the overall delta S for the system will be less than 0. That's my prediction. So the prediction is going to be negative, or delta S is less than 0. You can say that. So the instructions, will delta S be positive or negative? It'll be negative. Let's calculate it. Let's see. So the entropy for H2O liquid, let's down here, we're going to look for H2O liquid, and I'll write it up here, is 69.91. We're going to add that to the entropy for CO2 gas, which is over here, which is 213.8. We're going to subtract from that the entropy of the CH4, which is 186.3, plus the entropy for O2, which is 205.03. And let me go back. So here's my calculation. So I'm going to go 69.91 plus 213.8. And I'm going to subtract 186.3. And I'm going to subtract 205.03. And I get minus 107.62. So my calculated value is 107 minus 107.62, which agrees with my prediction. So that's it. I want you to do the second one, practice that. And this is a worksheet I want you to upload. I want you to upload this one. So upload worksheet number 23, that's in instructions. And let me I'm back live. So thank you for watching. And that's all for chapter 16.3. And I'll see you next time. Goodbye.